I hope by now that you have downloaded our free simulator program from this website. It will make it much easier to follow the tutorials as we continue. To gain the full benefit of the tutorial, you should use the simulator to experiment with circuits of your own. We have seen various waveforms which our oscillators have been able to create so far. For the purpose of further instruction, the simulator has its own waveform generator. It has its own built-in power supply which you can set, and you can also choose between triangular waves, sine waves or square waves. You can set the frequency of the wave in cycles per second, called hertz. Here we have two waveform generators. As you can see, we can set the waveform, median, amplitude and frequency. We start the simulator to show the waveforms generated. The sine wave is typical of the waveform created by an electric generator or dynamo. The electricity supplied to your household typically arrives as a sine wave with a frequency of 50 Hz and a voltage of 240 volts. This is referred to as alternating current or AC because the polarity switches from positive to negative every cycle. This current is simulated here, but the simulator has been slowed down to 1/10 speed to show the waveform. Suppose we want to use our household electricity to power a 12-volt device requiring direct current. The first thing we would need would be a transformer. We know that a coil around a soft iron core will cause the iron to be magnetized. An input alternating current would cause the polarity of this magnetism to alternate. This in turn induces an alternating current in the output coil. By varying the number of loops in the input and output coils, we can step the voltage in the output coil higher or lower than the input voltage. For our purposes, we require an output voltage of 12 volts. Suppose with our transformer we now have an alternating current of 12 volts. How do we convert that to direct current or DC? Consider this circuit. Because the diode only allows current to flow in one direction, the voltage of the capacitor builds up. Here the simulator is running at 1/10 speed. We see that the capacitor becomes like a battery and in due course is able to provide direct current to the LED. Notice that we are losing half the energy from our generator as no charge is accumulated from the downward half cycle of the input wave. This will be solved by the full wave bridge rectifier. Converting alternating current to direct current is called rectification. In this example, either D1 and D2 are both on and D3 and D4 are both off, or alternatively D1 and D2 are both off and D3 and D4 are both on. While the wave is positive, electrons are flowing anticlockwise. D3 and D4 switch off and electrons flow through D2 and the load and back through D1. While the wave is negative, electrons are flowing clockwise. D1 and D2 switch off and electrons flow through D4 and the load and back through D3. So electrons are always flowing through the load in the same direction. This arrangement of diodes is called a full wave bridge rectifier. Placing a capacitor across the output of the bridge rectifier has the effect of smoothing the current. During peaks, some of the charge is stored and is available during troughs. The bigger the capacitor, the smoother the current. We shall now look at sound waves. The wave generator has been set to produce a sound wave which we will play through the speaker. A sine wave with amplitude of 10 volts has been set. The time interval of the wave generator is set to 2273 microseconds. So the frequency is 1 million divided by 2273 equals approximately 440 cycles per second. This is the frequency of middle A on the piano. This is the sound that is generated. It sounds like middle A or A4 as a pipe organ might play it. In that example, the current was sufficient to drive the speaker. But what if the current were too small for the speaker to play an audible sound? Here the wave generator is producing a 440 Hz wave with voltage amplitude of 50 millivolts. Passing a current from this voltage through an 8-ohm speaker is not sufficient to make the speaker sound. So we create a simplified amplifier. The capacitor is continually charging and discharging in time with the wave generator, and this causes fluctuations in the current at the transistor base. These fluctuations are amplified at the collector by a factor of 99. Passing the current through the speaker from the collector will cause the speaker to sound. We are running the simulator at 1/100th of normal speed in order to see the waveforms. This is the sound generated, which is similar to that produced before. Doubling the frequency of the wave to 880 Hz produces a note 1 octave higher, or note A5. What happens if we have two synchronized waves in series? We see that the frequency remains the same, but the amplitude or loudness doubles. Remember that frequency controls pitch and amplitude controls loudness. In this example, we are playing the two notes A4 and A5 together. Remember that in this case, the middle of the oscilloscope represents a zero current. Notice how the waveform on the right is the sum of the two waveforms on the left. Composite waveforms like this provide musical chords, and more complex still, provide music and speech. A piano tuner has a tuning fork constructed so that when it is struck it will vibrate at a known oscillations per second, giving off a sound. Suppose the fork vibrates at 440 Hz and he wants to test middle A on the piano, which should also vibrate at 440 Hz. If the key is slightly out of tune, the two waves will not quite coincide, so will cause the amplitude or loudness to oscillate. At times the two waves cancel each other out, causing quiet, and at other times the waves add together to cause loudness. In this example, the piano is vibrating at about 440.5 Hz. The resulting sound is this. In this test, we have included a variable resistor or potentiometer to vary the current passing through the speaker. As the resistance changes, the amplitude or loudness changes. Note that the frequency remains constant. This form of wave is called amplitude modulation, or AM. On the other hand, here we have a wave with a fixed amplitude, but the frequency changes. This is called frequency modulation, or FM. We have heard about AM and FM in relation to radio waves, which we will encounter in a later part of the tutorial. Now let's process sound waves from a microphone. The simulator has a microphone facility. You can record sound as a .wav file and then play the recording into your project. We show that first. Click on the microphone, click Start, record a sound into your microphone, click Stop. You may play that back. The file that you have created has been stored where your program runs, and it has been given a name lesound.wav. You may import that into your project. We can import any .wav file into our project by first placing it in the directory where the program is running. We return to our earlier project and replace the wave generator with a microphone. Here we will import a few piano notes. Once we have imported the file, we can display the frequency of the recording. This file has been recorded at 48,000 samples per second. For a good recording, we need to slow our simulator down to 1/10 or 100th speed. The microphone is of electromagnetic type, which means that it converts sound waves into voltage fluctuations of a few millivolts. So the incoming waves need to be amplified before playing through the speaker. We see that amplification is taking place. Here is the sound generated at an earlier trial. That concludes this part of the tutorial. The next part of the tutorial will be on the inductor.